Some more examples on the limiting or clipping circuits, but here in these examples we are going to consider practical diodes with constant voltage drop model. So we'll assume that the diode operates if the voltage across it is higher than let's say 0.7. So we'll assume here constant voltage drop model for the diode, which means that the diode will be on if V diode reaches 0.7. If the voltage across the diode reaches 0.7, it will be on. If the voltage of the diode is less than 0.7, then the diode will be off. Okay? So let's start with the first one. The first one again is a simple circuit. This is V input, resistance, diode, and this is V output. We'll say again, ask a question that when would this diode be off? This diode will be off if the voltage across the diode is less than 0.7, right? So we'll say that the diode is off as long as V output is less than 0.7. In this case, the circuit will look like this: V input, V output, and the diode is open circuit, it's off. In this case, V output will be equal to V input, and thence we can plot the relation between V input and V output as following. When V output is less than 0.7, the relation will be V output equals V input, which is a straight line. So here the diode is off, and above this point it will be on, right? So here, when the diode is off, the relation between V output and V input will be a straight line with the slope 1. It's important to write the slope because in some other circuits we'll see that the slope will not be 1. Okay? And then when the diode is on, we have to ask ourselves, what about the other region? When the diode is on, it will be working as a battery of 0.7, and in this case the output will be exactly 0.7. So the output will be clipped to 0.7. That's why we get here a curve that is a straight line of slope 1, then it will be clipped at 0.7. If we reverse the diode in this example, you will find that this diode will be off, and this is always, again, I'm repeating it, ask yourself first about when the diode or when the whole branch will be off. First start with the off case. It's easier to start with the off case. The diode will be off as long as the voltage here is higher than the voltage here by negative 0.7, right? So in order for the diode to be on, you need the ground to be higher than this voltage by 0.7. In order for the diode to be off, and this is the question that we ask, the output must be higher than what? Higher than negative 0.7. Why? Because this terminal is connected to 0, right? If the terminal here, the negative terminal, is higher than negative 0.7, then this diode will be off. So in this case, we say that the diode will be off as long as V output is greater than negative 0.7. Why negative 0.7 again? I know when you reverse the diode it might be confusing a little bit. Why negative 0.7? Because you need, if this is connected to 0, you need here to be negative 0.7 in order to operate, right? If this point is higher than negative 0.7, then the diode will not operate, the diode will be off. So as long as V output is greater than negative 0.7, the diode will be off, will be open circuit, and again we will get a relation between V output and V input, that V output equals V input. So the critical point here is negative 0.7. When V output is greater than negative 0.7, the diode will be off, and V output will be equal to V input, straight line. In this region, when the diode is off, V output equals V input, straight line with the slope equals 1. On the other hand, when the diode is on, of course, if this is negative 0.7 V output, then this will be negative 0.7 V input. When the diode is on, what will happen? It will operate as a battery. The direction of the battery will be in this direction. right? Negative up, positive down. And this battery has a value of 0.7. This is the output. This is R, this is the input. What's the value of the output in this case? First, this happens when V input is less than negative 0.7. This happens when V input is less than negative 0.7 volt. In this case, V output will be clipped at negative 0.7 exactly, right? V output in this direction, positive here, negative here. It will be equal to negative 0.7. So the output will be clipped to negative 0.7. So this is the second circuit. The third circuit combines both circuits together. So we have two parallel branches. The first branch will give us a characteristics like this. So the first branch, it will be on when V output reaches 0.7. So it will clip the output at 0.7. The second branch will clip the output at negative 0.7. So that's why you expect that the output, once it reaches 0.7, this diode will be on, it will operate as a battery, it will fix the output at 0.7. When the output reaches negative 0.7, the other diode is going to operate, and it will operate as a battery, like the example there, and it will fix the output at negative 0.7. In between these two levels, when the output is lower than 0.7 and higher than negative 0.7, both diodes will be off. And if both diodes are off, then V output will be equal to V input in the middle. I will not do it in details, but it's a combination of what we said. Okay? So the first diode will limit the output, it will clip the output at 0.7. The second branch will clip the output at negative 0.7, because when it operates, it will operate as a battery with negative 0.7. So it will clip the output at negative 0.7. In between, both diodes will be off, and V output will be equal to V input. You can add a battery as the first example that we solved in the limiting circuits. You can add a battery with the diode. In this case, if you add a battery with the diode, and let's assume constant voltage drop model, in this case, you will ask yourself, again, when would this diode be off? When would this diode be off? The diode would be off if the voltage here is less than 0.7 plus the voltage here. Why? Because in order for this diode to be on, you need to overcome the negative voltage by 0.7. The negative voltage is 5 now. The negative voltage is 5, right? So this diode, we have 5 volt connected here. So the voltage of the cathode is 5 volt. So as long as this is V output, so the voltage here is V output, this is V input, this is R. As long as V output is less than 5.7. Why 5.7? Because for this diode to operate, you need to have a voltage here of 5.7. When V output is less than 5.7, the diode will be off, open circuit. And if the diode is off or open circuit, no current in the circuit, and in this case V output equals V input. So when the V output is less than 5.7, when V output is less than 5.7 in this region, V output will be equal to V input, which we can plot as a straight line with a slope 1. And again, when V output reaches 5.7, V input also will reach 5.7, because this is a line with a slope 1. So here 5.7 and 5.7. Once V output reaches 5.7, the diode will be on, short circuit. And if the diode is on, V output will be fixed to, if the diode is on, it will operate as a battery of 0.7, right? We use the constant voltage drop model here. So when the diode is on, it will operate as a battery of 0.7. So V output in this case will be fixed at 5.7. Whatever the value of V input, even if the value of V input increases, V output will be clipped at 5.7. What about the difference between V input and the V output? The difference will go to the resistor here. This resistor will take the difference between V input and V output. V output will be fixed at 5.7, okay? And the resistor will take the difference between V input and Vi. Of course, you can solve all these examples again using the piecewise linear model. Using the piecewise linear model. I'm going to try just to give you a hint of how to do that, but you can do it by yourself. When you use the piecewise linear model, the only difference will be when the diode is on. When the diode is on, let's operate on this same problem. When the diode is on, it will be represented not only with the battery, it will be represented by a resistor RD and then 0.7 in addition to the 5 volt here of the source that we added. In this case, when the diode is on, when the diode is off, it will be the same thing, yeah? No difference. No difference. When the diode is off, V out equals Vm. The only difference is when the diode is on, V out equals what? V out equals what? V out is the voltage across this branch, right? So it will be 5.7 plus the voltage here. It will be 5.7 plus the voltage across this resistor. What is the voltage across this resistor? The voltage across this resistor is the difference between V input and 5.7, and then you do voltage divider between these two resistors. Take Kirchhoff voltage law. Kirchhoff voltage law, V input equals the voltage here across this resistor, plus the voltage here, plus the voltage here, which is 5.7. The difference between V input and 5.7 will be divided between these two resistors, right? Using the voltage divider rule. So the voltage across this resistor will be V input minus 5.7 V input minus 5.7, and then you multiply by this resistor over the sum. Multiply by RD over R plus RD. This part gives you only the voltage across this resistor. And then you add to it the 5.7 here. It gives you the output voltage complete. So the only difference between the constant voltage drop model and the piecewise linear model is that you will have a resistor here, and while calculating the output voltage, you have to take care of the voltage across this resistor in any way that you learned in the circuit analysis. Last example in this video, if we consider two Zener diodes, and this is a famous example, two Zener diodes connected opposite to each other. So let's think about this circuit. Ask yourself, when would the output cause the whole branch to be off? So this branch can be on in two cases. First case, if the current goes in this direction, so diode Zener number 1 will work as a regular diode in the forward region, and Zener number 2 works in the breakdown region. In this case, in order to work in this direction, you need the output to reach the forward voltage of this, which is 0.7. Let's assume constant voltage drop model again. So in order for Zener number 1 to work in the forward region, you need at least 0.7 volt. And in order for this to work in the breakdown region, you need V Zener. You need a voltage of V Zener. Okay? Or this branch can work in the opposite side. Zener number 2 works in the forward region, and Zener number 1 works in the breakdown region. In this case, you need V output to go below negative 0.7 of this diode and negative V Zener 1 for the breakdown of Zener number 1. So let's go slowly here. Let's go slowly. We have the circuit. It looks like this. This is V out. And let's assume constant voltage drop model for both diodes, okay? With 0.7 battery, and let's assume that Zener number 1, it has a breakdown voltage of VZ1, and Zener number 2, it has a breakdown voltage of VZ2, okay? So, we ask ourselves, when would this branch be off? This branch will be off branch will be off as long as V out is not enough to operate this branch in the forward or in this direction, nor in the other direction. In order for V out to operate this branch in this direction, you need V out to be equal to the forward voltage of this in order to operate in this direction, in order for the current to flow in this direction. You need V out to be equal to the forward voltage of this, which is 0.7, plus the breakdown voltage of the second one, which we call V Zener 2. In this case, the branch will operate in this direction. In order for the branch to operate in the other direction, you will need V out to be negative, of course, right? In order for the current to go up from the ground up, you need V out to be negative. So you need V out to be negative the forward voltage of this, so negative 0.7, negative the breakdown voltage of this, so negative V Zener 1. But what happens if this branch is off? So the branch, we say that the branch will be off if V out is not enough to operate the branch in this direction nor in the other direction. So it's less than 0.7 plus VZ2 and it's greater than negative 0.7 negative V Zener 1. In this case, the branch will be off. And if the branch is off, means open circuit, V output will be equal to V input. So here, the two limits of this branch is 0.7 plus V Zener 2 and negative 0.7 negative V Zener 1. Between these two limits, the branch will be off. Here the branch will be on in the forward direction, and here the branch will be on in the opposite direction. If the branch is off, V out will be equal to V input. So we'll get a line, straight line, with slope 1. Once the input reaches this point, VZ2, 0.7 plus VZ2, okay, the branch will be on. This diode is going to operate in the forward direction, and this will operate in the breakdown region, and then what we'll get, when the first diode works in the forward direction, we'll get a battery 0.7. When the other one works in the breakdown region, we'll get a battery of VZ2, so the output will be fixed or clipped at 0.7 plus VZ2. On the other hand, if V input is negative and reaches to, while we are working in the off region, V input reaches to negative 0.7 negative VZ1, then it will be enough to operate this branch in the opposite direction. This branch is going to work in the opposite direction. When it works in the opposite direction, the diode number 2 will operate in the forward region, so it can be replaced by battery in this direction, 0.7, and the other one, diode number 1, will work in the breakdown region, and you can replace it by a battery. And as we said before, the battery should be opposite to the current, right? So if the current goes in this direction, you replace this with the forward battery, which is 0.7, opposite to the current, and the other one will be also opposite to the current, but its value is VZ1. In this case, V output will be clipped to negative V0.7 negative 0.7 minus VZ1. And this will be the transfer function of this circuit. We'll stop here in this video. Of course, we solved many problems now with constant voltage drop model. I urge you to try to use the piecewise linear model. In this case, you will find that for all the problems, you'll find that instead of clipping the output exactly at a certain value, the output will have a slope. The output will have a slope like this. This slope comes from the voltage divider between RD and R, and the resistance R. So there will be a voltage divider multiplied by some voltage here. This voltage divider will cause the output to increase with the input, okay? without being clipped at a certain level. You try it by yourself, but you'll find that we'll get a slope here instead of a horizontal line, instead of hard limiting the output at a certain level. The output will be limited, but with a certain slope that is proportional to RD over R plus RT. You try to solve all the problems again at home using the piecewise linear model to see the difference between what we got and if we use the piecewise linear model. We'll see you in the next video, inshallah.